Maybe a quick introduction, and then we're just going to basically write some code and run it. Quickly, my name is Jamie Grier. I'm the Director of Applications Engineering at Data Artisans. Basically, that means I help people to be successful in getting Flink applications into production, whatever that means. That's basically my core mission. So I help a lot of people with their production projects with Apache Flink. Background in stream processing for a while. I worked at Twitter on the streaming computation team before I joined Data Artisans, so it's kind of been my field for a little while. All right, so the quick overview. I'm going to blaze through what is Apache Flink since this is Flink forward. I think I'll pretty much skip over that part. What is stateful stream processing? What do I mean by that? Then we're going to do some windowed computation over streams and look at the results and see if we can do this stuff robustly and what it means, whether we can or whether we can't. And then we're going to talk about robust time handling, failure handling, planned downtime, and how we maybe upgrade a cluster or upgrade our code, and also how do we reprocess data. These are all very sort of important production concerns if you're really doing stuff in the real world with Flink. So we're going to go through all these things. And I'm going to skip this first part. So stream processing, in a nutshell, as I think most of the people in this room know. There's some experience with stream processing, I assume, from the audience. Yeah. So basically, at a very basic level, you've got a stream of data. It's an unbounded data set. You've got some computation that you want to do, and you've got maybe streams as output. You have other things as outputs as well, but for the context of this, let's call it a stream. This is pretty basic stuff. Stateful stream processing, though, is a little bit different in that in this previous model, it's quite simple. The output can only depend on the input. There's no state. In a stateful stream processing model, you have a data stream as input. You have some amount of state you can update, and you have output. The input and output is actually decoupled in the sense that output isn't always the direct result of input. So it's the current input and maybe all the previous data. Any state that you want to keep, you need to be able to do that. So the important thing is when you go to this model, the stream processing framework you choose has to be able to manage that state for you fault tolerantly. So in the face of failures, in the face of errors in your code, node failures, machine failures, you need to be able to rely on that stateful computation you're doing still being accurate in the face of all of those things. So you need to be able to provide consistent, repeatable results even when things fail. So we're going to talk a lot about sort of the robustness of how we deal with managing state and what happens if we don't as well. And then a more complex example is, in the real world, we don't just have one input stream, an operation, and some output stream, but we have graphs of things. So in this case, we have maybe Kafka as an input, maybe some files from HDFS or RabbitMQ. A few different operations, map filter, join and sum, maybe window, and then we're going to write the output, maybe to Cassandra in Flux DB. And then finally, so we build these graphs of operations. And then finally, we don't just have one instance of this graph, but we want to use a bunch of machines because we have a high input rate, or we need to scale the computation because the computation is really heavy. So we want to be able to easily take that sort of graph of computation and use a whole bunch of machines to sort of to be able to actually compute the results that we need to keep up with the data stream or the computation we need. And in stream processing, basically always you're, for the most part, dealing with not soft real-time requirements. You really need to keep up with the data rate as it's coming in because it's continuous. It's very different than the batch world in that sense. So you need to be able to scale out. Okay. So let's get started with some code. So what I have here is I have a data generator that I'm going to walk you through really quickly, and then we're going to start to write some code. The data generator I already wrote. I'll just walk you through the code real quickly so we see what it is. But basically, it's going to generate some waveforms, and then we're going to do some interesting things with them. So this down here is a data generator, okay? And I'm not going to spend a lot of time on this code so that we'll have time for the rest. But basically, you take an input source. This is just a source of basically, we're just generating events with a timestamp. And then this operation here is we're going to map that into sort of a sawtooth pattern. And the output of that is going to drive two other waveforms, a sine wave and a square wave. If you jumped into one of these functions just so you can see what they are, they're very simple things, right? So this is just something that this is the square wave function, so just giving some input value, it maps it to basically, how does it work here? So we have, it generates a square wave, so you go from whenever the value of the input is over 4, you go to 1, and when it's not, you go back to 0. So it's just a total square wave, flip-flop. So all of these things are very simple, just like this one, right? So you just have all these generation things. And then in the end, if you want to just run this data, or run this job, this Flink job, we don't even have to have Flink installed. We actually just have a Maven dependency here, and I can just run this right here in my IDE, and I'm running a Flink job. And if we look here, let's see, whoops. What I wanted to do, sorry. I just want to show you the data. Just quickly so we have a sense of what it is, right? So basically we just have a timestamp, some key, temperature, pressure, or door, and some value. That's all it is. And we just have a bunch of these coming in. It's one big data stream that we can sort of pull out different pieces of data, as I'll show you, based on keys. The other thing I want to do here is actually run, I'm actually going to start up a Flink cluster locally, just like that. I'm going to run influx. Because we're going to run influx, we're going to actually throw some data in there so we can visualize it. And I'm going to run Grafana. So we can have a way to look at these things. And just so we get a little bit more of a sense of this data, rather than just bring it out to the screen, I'm going to start to do something different with it. So let's, instead of doing that, let's take that data stream and add a sync. And we're going to write this to InfluxDB. Okay, this thing is also very simple. It's something I wrote just for this demo. It's not like a production quality Influx DB sync. It's just, the very basic thing. But essentially, for every single message, you get this invoke call, and you can do whatever you want with it. In this case, we're going to write it to influx here. I don't know if you guys can actually see that anyway. Yeah. So simple. So now we should be writing data to influx. Run this guy, and maybe we can look at it and see what the data actually looks like. Let's see. Or not. That's why. I'll be worried for a second. Okay, so there we have this temperature sensor, we have a pressure sensor, and we have this door sensor. We have our sawtooth, our sine wave, and our square wave. Okay, so far so good. That's kind of the data set we're starting with. So now what we want to do, the first thing we're going to do with this, that's something you do really commonly in stream processing, is we're going to window it. The reason you do this is if, say, you just want to compute a sum, just logically, you can't really compute a sum over an infinite data set. It doesn't make any sense. You'd have to wait forever in order to compute the sum. So instead, you define windows, and then you do some sort of analytics over the window. So I want to show you kind of what that looks like in Flink next. So we can take this stream we've already got defined, and first thing we're going to do is key it. Okay, there's actually a field in the data called key, which is why I referenced key right there. It doesn't have to be called that, but that's what it's actually called. So then we're going to key it by key. We're going to define a window. And then we're going to sum the value, which is another field reference to the data itself. And then let's write this to influx as well. Summed sensors. And have a look at that. Let's see what it looks like. Okay. So in this case, we have let's just look at this pressure wave. The input data is on top, then the summed data is the next row down, and they correspond to each other vertically. So if we looked at, say, this pressure wave, it's a sine wave, right? It repeats on a 1 second period, and we're summing it. So if I look at that and we sum over a sine wave, what should the total be? If we sum all the data points in a sine wave? 0, right? Exactly. It should be 0. And not sort of 0. It should be exactly 0, right? Every single time it should be exactly 0. But when we look at this output, we're sort of hovering around 0. And there seems to be some sort of inaccuracy or non-determinacy here, right? Does anyone have any idea why that might be? OK, so what's happening here is this is going to kind of give us an opportunity to look at event time versus processing time and say, what is this all about, really? And this is one of the better demonstrations I've found to really show that like doing things in event time is how you get accurate computation. Just that alone. Like if we do it this way, we have errors. If we do it with event time, you're going to see that we can fix this. And I actually have a slide about this that makes it clear what's going on. Let me see if I can find it. OK, so what we're doing now, because I don't have event time enabled in Flink, is we're just windowing and processing time. And this is really typically done, actually, in the industry and in many other frameworks. And so what we're doing is the green represents sort of the input data, and the green numbers represent timestamps in the actual data itself. And what we really want to do is we want to bucket these things into 1 second windows based on what the timestamp in the data says, right? As opposed to just when it arrived at the machine. But what we're doing instead is this. So the purple represents processing time. And we have this mismatch or misalignment between like when the data sort of, it's a little bit late, it's a little bit indeterminate, it gets backed up in Kafka, it gets backed up in some other system, kind of arrives later, comes a little fast, comes a little slow. We want to get rid of all of that, right? And so we want to do this correctly. So what we want is this. We want to look at the data. We want to actually draw windows around the, we want to make sure that we window the data based on the timestamps that are in the data as opposed to any other way, right? And this is what gives you total repeatability. It gives you, it's going to take out all the errors we see. If you run this whole thing at 100 times the speed, you're still going to get exactly the same answer. If you did that with straight processing time, you're going to, if you're summing and you run 100 times as fast, you're going to get a 100 times bigger number. So all this stuff around event time is what makes this stuff accurate, robust, and repeatable. OK, so to do this in Flink, we should just be able to turn on event time. And those errors should go away. So you set the time characteristic, which is what it's called, there. And run this guy. And let's see what happens. OK. So that's basically all there is to it. So now, if we run this data a lot faster, a lot slower, we pause something for a while, any of those things, this is all totally repeatable, and now we can do accurate computation. It's easiest way to see it because it's a sine wave and you're summing over it, so you know what the answer should be. But this exists in every analytics system if you're doing processing time. And so this just clearly shows that if you do event time, you can get accurate results. And it's very hard to get accurate results any other way. So that's the first thing I wanted to demonstrate. Does that make sense to everyone? We're all OK. All right. So what's next? I guess the way I look at it is doing things in processing time just equals errors. And doing things with event time equals accuracy. There's a bunch of other stuff about event time, such as like really handling totally misordered data, things that really in the real world come out of order. All that stuff is also handled by event time. But this is sort of the piece of it I wanted to talk about today. OK. Whoops. OK, so the next thing I want to talk about is failure handling. And the way we're going to do this is we're actually going to run the same code. Actually, I'm going to add a little bit of code, and then we're going to like cause some failures to happen, and we're going to see what does happen. Let's see. So I'm actually going to disable this for demonstration, and I'm going to shut down the job. OK. And what I'm going to do here is, rather than running the IDE, I'm just going to run from the command line. And again, I'm going to, I think I already started a cluster. I have a cluster running. Should be able to see this. This is the Flink UI, by the way. It shows us we have a cluster running. We have one task manager. It's just running locally, so we have just a little bit of resource we can use to run jobs. And now what I'm going to do is I'm just going to submit the job we just compiled, the same one we've been using in the IDE. I'm going to submit it to the cluster. Just like that. And here we should find that a job is running. And here. So actually, I didn't show this before. I should have. This is what Flink turns your program into, basically. So this is the data flow graph based on that code we wrote, where we have an input stream. We have this generator. Then we have a sink, one sink to write out the sensor data. We have another thing that does some windowing, writes out to another sink. Basically, that's all visible here in this data flow graph. You have the test data. Here's your sawtooth, sine wave, square wave. This is all part of the generation. This assigned key stuff is part of the generation. We write the raw data out to a sink. This is the window function. And then we also write that out to a sink. OK? And we should be running, and we should be able to see data here. So one of the things I want to do, actually one more thing. One more thing. I'm going to add a little bit more complexity to this job. OK. Let's see. I'm going to grab this for time's sake. And I'll just walk you through it real quick. So I'm going to add one more input to this job. Oh. Make all the types happy. OK, so I just added one more thing to this job for a little bit of extra complexity, and so I can show off sort of, make it a little bit more apparent what state is in the system that we need to protect. So I added this here. This is very simple. We have a socket stream, which just means we're going to listen on a socket, and we're going to get messages. There's strings there. I'm going to turn that message. I'm going to parse it and turn it into a control message, which is just a very simple type here. What this is going to represent, though, this control message is going to allow us to, for some key, modulate the output of this whole thing. And we have this thing called the Amplifier Function, which is a simple Flink function. But what's neat about it is this is a really common pattern, actually, and it's really useful. Is we're going to take two streams, and we're going to have the main data stream, and we're going to have sort of a control stream. And then we're going to feed both of these into a single operator, which is this amplifier function. And we're going to keep state for every key. And we're going to be able to modulate independently all of these waveforms. So for each, essentially the state is this. For each key, what amplification factor should we apply for that data that has that key? Make sense? And so what we can do with this when we run it, let's see, let me run it out here. There's nothing running. Run our job. If we refresh this guy, we're going to see we have a little bit more complex job graph still. OK? So this is this new input we added. And we have one more sync, which is in the code we're going to do this amplified. We're going to amplify these input streams, and we're going to write them out to this as a measurement in Flux DB called amplified sensors. So you can see that addition on this job graph here, which is this lower part. But this is our whole job graph now. OK, so what can I do with this? This is the point right here. So you can do this. Temp, I can say use a amplification of 1, use a magnitude of 1 for the sine wave, or that's the sawtooth wave. Pressure 2, square 3. and I actually can control now dynamically this output of one of these operators. So it's actually a really interesting pattern, right? Able actually to reach into the topology and change the output of one of the operators by using the second control stream. Okay. So now the topic we're on is failures. So what I want to do is actually just, let's cause a failure and see what happens. I'm just going to kill the task manager, which is the process in the system that runs the user code. I'm just going to reach out there and kill it. So it's dead. You see there's no data coming in. I'm going to zoom out a little bit here so we can see what's happening. And what's happening right now is Flink would recover like immediately if there were more resources. Say if we're running on Yarn or Mesos or something, it would just go get the resources, and we had already recovered. But actually, I'm sort of playing the role of the resource manager here, so it's not going to be able to recover until I add one more task manager to the system. So it's trying to recover. If you looked at the Flink UI, you could see this job is in this restarting state. So Flink's trying to recover, so it's waiting for resources. I can do a demonstration in a second how quickly that recovery happens if I'm not in the loop. But so what I'm going to do is I'm just going to run this task manager. What's the time? Start. Now we have resources. We should be able to schedule that job. And it should go back to running. And in fact, it did, which is great. However, it doesn't look very good. I mean, what's happened here is we've lost a whole bunch of data, right? If you look back, you can look back even further. I just zoomed out on the time series. So you can see there's this huge gap here. So the whole time we were down, what really happened is that we lost our state, which is bad, right? This is, this wouldn't be that uncommon kind of before, but in this modern world where we have robust stateful computation over streams is what we're trying to accomplish, we can't have this happen. If there's a failure, we need to be able to compute the exact same result as if nothing ever happened. So the way you do that is through Flink's checkpointing. And I have it turned off basically just for this demonstration of like what happens when it's no good. Let's see. You would never run this way in the real world. I just wanted to show you, like, this is the problem we're trying to solve. And it's worth pointing out, I think, as well, that in this job graph, many of these operators are stateful. And if any of them aren't recovered properly, you'll see on the graph right away that there's a glitch. So the waveform generator is stateful. The initial timestamp generator is stateful. A couple of the waveform generators are stateful. And certainly the state we're holding that controls the modulation of that output in that amplified sensor, that's obviously state. So we've recovered, but we've lost all that, right? And if we look especially down at this amplified sensors thing, we're right back to where we started. We didn't recover to the correct state. So now if we do this again, though, so I'm going to reprogram this to the setup I wanted, right? Maybe we can zoom in a little less. We can see that we're, again, running, I guess, mostly focus on the amplified sensors output there. And I can actually cause a failure, by the way, just by giving some bad data here. So if I said this is a Flink, that's a failure. You can see just for a second, we're going to lose our state. Oh. Did I not? I think I might not have compiled the last version. Sorry. Okay, hold on. Okay. Try this one more time. Okay. So we have this state where we have one of the waves has an amplitude of 1, the pressure wave has an amplitude of 2, and the square wave has an amplitude of 3. So we're back into this state. I said I should be able to cause a failure just by doing this. and it should just recover. But it recovers so quickly we don't even really see it. But notice that actually was a Flink failure if you went and looked at the logs. But I'll do it with the task manager again. But notice it's as if nothing ever happened, which is what we want to see. But I'll go and actually kill a task manager so we can make it a little more obvious. Okay, we're losing data. You see we have a data gap. If you look at all of the graphs, there's nothing happening, and we have this amplified sensor stuff where we're not receiving any data. So when I bring this task manager back into the cluster, what I want to see is that it's as if nothing ever happened, and we come up in exactly the same state we were in before. So let's see. Oops. Let's see what happens. There we go. So that's, thank you. yeah. Yeah. So that basically shows full recovery of a stateful computation. The next thing I want to talk about is based upon that. And I think, yeah, we have a few minutes left. So back to Keynote. The next thing we want to talk about is downtime handling and data reprocessing. These two sort of go together, and I can certainly make them go together in the amount of time we have. So downtime handling, this is going to be where, let's say we just wanted to upgrade the Flink cluster, or we wanted to change our code and bring it back up with new code or something like that. We fix a bug. Maybe we want to like reprocess some data because, again, like we had a bug in our code, or we became interested in some new part of the data, and we want to change our code a bit and recompute everything we've already processed before. The way you can do that in Flink is called Savepoints. And so it's very similar to what we've already seen, but in this case, it's to handle, you can actually completely bring the job down, destroy the cluster, or move that computation to a different cluster, and then I'm going to show you how to do that here. So basically, all we have to do is we have this running job, and there's this job ID is important for this. So we are going to make a save point and give it the name of this job. And it's going to save that save point into this location, which will be, I'm just going to copy. Okay, so we're running. I'm going to do something a little bit crazier this time. So I'm just going to destroy the whole cluster. So I'm just going to blow away everything. There's not a Flink cluster. If we go to this board here, yeah, there's nothing. It's this in this UI. So what we could do now is we could build a new cluster. Maybe it's the latest upgrade of Flink, some patch release. Maybe we're going to change our code at the same time as well. Maybe we're going to move this job to a different cluster. There's no cluster now at all. So I'm just going to create now. What we want to do, though, is wouldn't it be cool if we could just resume this computation as if nothing ever happened, even though there's no Flink cluster right now? And it's yeah, that's what we'd want. That would be ideal in the real world. If you can do this kind of stuff, you solve a lot of production-oriented problems, right? Stop, upgrades, code changes, all of this kind of stuff, reprocessing of data. So I'm going to start a Flink cluster. Okay, it's running. Here's a Flink cluster running, I believe. There it is. It's got some resources. And what I'm going to do is I'm just going to start my job, same as before. But this time, I'm going to reference this save point. And essentially what this command says is run this job, but resume from this state. And here we go. What we should see is it's as if nothing ever happened. I didn't do it quick enough. There. So we've actually recovered completely. It's as if nothing ever happened. If you back up, let's see. Let's back up a little bit. Ever since this was our downtime, this was the beginning of our example where I was actually trying to show you that there was a problem if you didn't have checkpoints enabled. Ever since then, this just recomputed everything and caught back up to real time. Another example of this is say we wanted to like change our code a little bit. I'll just do something really visible. I'm just going to change the length of these waveforms, but that represents a code change. If I compile that, and I shut this guy down, and I launch from that save point again, We can actually sort of reach back in time and recompute everything since the time I made that save point with new code. So I'll do that, and we should see this all just gets recomputed. Oh, so this was the actual point where we had a save point. So that is how you'd handle downtime, planned downtime, upgrades, and data reprocessing, which comes up in the real world all the time. Like, when I change my code, how am I going to go and reprocess all this stuff? Because that's really what you end up doing a lot of the time. OK. Let's see. Downtime, data reprocessing. I guess we actually got to the end. Usually that takes me quite a while. So yeah, at Data Artisans, we are hiring. So if you're interested in working on Flink or working on this kind of stuff, you should let one of us know. And that's all I have. So maybe we could take some questions.
Wow, that's a cool mic. So can you explain the relationship between save points and checkpoints? It looked like this in the demo, you asked for a save point.
Yeah.
And then you let it run for a little bit, just because, and then you killed it.
Yeah.
And then when it restarted on the save point, what happens?
Yeah, so the checkpointing mechanism is Flink's basic fault-tolerant mechanism. So every so often you make a checkpoint. You do it in an asynchronous fashion, but essentially it's a global snapshot of all the state in the system, right? You can think of it as just like a world, like a snapshot of a consistent point. And Flink does that periodically all the time. Normally what happens is when you've made a new consistent checkpoint that you can recover from, you can delete the previous one, right? So you only ever need one good one that you can always fall back to in the normal failure cases. So all a save point is really is a checkpoint initiated by the user, given a name that you can manage, and you manage its lifetime. So once I've made a save point, that state snapshot sticks around forever or until I get rid of it, okay? So you can make them at different points in time whenever you want, and then always return to that state. So imagine what you're really doing is you're just going back to an exact previous state of this whole computation, which is actually pretty cool, right? So when you do that, say you're reading from Kafka, one of the things that's in your state is what's the current Kafka offset, right? So that's how you know where in the stream you were. And the rest of the state is all the computation. Like if I'm doing group by key and sum, it's all the counts, all the current counts for all the keys, all the windows that are in flight, all of the state of the computation you're saving off. And so you make those whenever you want, and you can travel back to those and resume from there whenever you want. So when you say Flink run from save point, it literally just runs your Flink job. The first thing it does is it grabs that save point, the checkpoints, referenced by that save point, loads that state, and then runs your job. So it's basically it's the normal checkpoint recovery process, but you initiate it. So a typical thing you do is like, if I have to shut down, I'd say Flink, make save point, stop whatever I need to stop, upgrade code, whatever, and then Flink run from save point, and everything comes back up like nothing happened. Yeah. Does that make sense?
Yeah, hello. So working for a company that has extensively used Storm, Apache Storm was basically sent here with a mission to find compelling reasons to make the switch from Storm to Flink. So it's actually a good thing that you're the one giving the presentation, since you seem to have been working at Twitter. So maybe taking the features that you presented during the presentation, so where do you think the Storm lag behind? Because they've been adding some stuff recently, back pressure, and also a windowing API, and I think the snapshotting will be in one of the future releases. So just basically, could you summarize in a few?
Yeah, I think the big difference is, there's always been this large performance difference between the two. Beyond that, the semantics, we have exactly one semantics with regard to all the state we're computing, right? So all of this state is recovered in such a way that's consistent with the input stream, so that if you're just doing something simple like counting, for example, you're never going to double count anything.
And that Trident API Trident on top of Storm wouldn't.
Trident is a little bit different as a layer on top of Storm. I don't have a whole lot of experience with it. For example, no one uses Trident at Twitter, so I don't have a ton of experience with it. But yeah, it's more of sort of like this micro batch model. And so they kind of the whole batch either succeeds or not. So yeah, it has some of those properties. It doesn't have the event time properties like I showed, like the first thing we did.
But I mean, it's part of the 1.0 release. I mean, like the windowing API, and also I think they added the possibility to consider like processing event time, and also like you can designate a key in your event to say, okay, this is the actual event time. But I mean, maybe it's a bit too detailed. I was just
Yeah. I mean, we could talk about it later,
okay.
but there's a whole, in order to actually make event time work, you have to propagate watermarks throughout the system, and there's all this stuff that has to happen.
Okay.
But,
well, thank you very much.
Yep, you're welcome. Anybody else?
Yep. In terms of determinism, in production workloads, do you often find that you take both event time and processing time and look at both? Because the way I see it, like event time is deterministic in terms of the computation itself, but the output is not necessarily deterministic because it can change over time, like when late events are processed, right?
Well, actually, as long as you're using event time strictly, everything is very well defined exactly what the output should be. What is interesting is when you might have both processing time concerns as well as event time concerns, based on your requirements. So often the two are still used together. And so the most common version of that would be event time is about making sure, like say you're doing some windowed analytics, you're computing some aggregate. Eventually, you'd say this is the final thing. Watermarks and event time is really about some notion of completeness and correctness. But you might have the requirement to, every second, update some downstream system. And that 1 second requirement is a processing time concern. So you might have event time characteristic, window in event time, but then in processing time, like every 1 second, have a trigger that sends the current count downstream. Mm-hmm. Those two things often go together.
And is there some mechanism to signal to downstream consumers of event time computations this notion of the fixed window and like completeness?
Inside Flink or outside Flink?
I guess both.
There's no way that's standard to sort of communicate watermarks, which is probably what you'd have to do to downstream systems. The watermarks inside Flink flow very naturally. So each downstream operation, each operation essentially has its notion of what time it is in event time. And it's done in this very reasoned fashion so that you get these consistent results. But there's no way to propagate that information directly outside of Flink to another system. You could build that, though.
Thank you.
Yep. You could also have the input system provide watermarks to Flink. That's supported today as well.
Hi, thanks. Good demo. In your demo, you're able to run your stateful job without defining checkpointing. And that's something that you cannot do in Spark. In Spark, if you have a stateful job and no checkpointing, it doesn't start.
Okay.
So is there any good use case for that, or is just
No.
nice?
I don't think so. I mean, I haven't seen anything in the real world where, like, I would never run Flink with checkpointing turned off. I haven't seen it used to do that. Because it's very, very efficient anyways, so it doesn't really cost you anything in most cases. So yeah, I would never run that way.
Jamie, can you share your source code from your demo? I found some of the stuff you're doing just interesting as a, demonstration type thing. Is that possible?
Yeah, it's already on GitHub now if you want to.
Oh.
If you search for OSCon demo or Data Artisans OSCon, you'll find basically the same version of code.
Yeah, okay.
Or come and find me and I'll point you to it.
Okay, thank you.
Yep.
Yeah, thanks a lot.
All right.